And you can see the gas slows down and shocks, but the dark matter just keeps going. And if I overlay the actual data on top of this simulation, that's exactly what I see. So this tells me that I need dark matter. The reason I know I need dark matter is because if I change the laws of gravity, I can't make this. I can't have gravity acting where my mass isn't. If my mass is over here and over here, then I'm not going to get gravity over here and over here. Someone might come along who's clever enough, and a few people have, and said, well, you know what, Ethan, I can invent a theory of gravity that does this. I can invent a theory of gravity that'll make, if I have mass here and mass here, it'll make gravity here and here. And I'll say, okay, but this isn't the only collision of galaxy clusters we see. We see Abell cluster 520, and we see the same effect. We see dark matter over here and over here, and yet the X-ray gas is over here and up here. And so if I make a theory of gravity that works for this configuration, it doesn't work for this configuration, and vice versa. And this is pretty strong evidence that dark matter has to exist. We need there to be some type of matter that doesn't emit light, doesn't interact with normal matter, isn't made up of protons, neutrons, and electrons, and yet that seems to be where most of the mass of the universe is. All right, so let's recap and say, well, now, if this dark matter exists, what is the universe made out of? Where is all the energy in the universe? Well, about 0.03% are in heavy elements. To an astronomer, a heavy element is any element that isn't hydrogen or helium. Anything heavier than helium, heavy element. Sorry, folks. All right, so yes, anything that's not that is what an astronomer calls a metal. Lithium, beryllium, boron, carbon, oxygen, nitrogen, metals. So, can't help you with that one. So that's actually an extremely small percentage of the universe. 0.03% of the universe is in heavy elements. We have neutrinos. These are tiny microscopic particles that atoms aren't even made of. Okay, these are just things that hardly interact at all. They're exotic standard model particles, and they are 10 times as abundant in the universe. They have 10 times the energy in the universe from heavy elements, from pretty much everything on this planet, all right, is in neutrinos. And the way you find it is you build giant tanks of water, and you wait for neutrinos from space to come in, hit the water, and then you see neutrinos and say, aha, now I understand neutrinos. But we do understand them pretty well. And it turns out they're 0.3% of the energy in the universe. Yes?
Can you tell me exactly how neutrino telescopes work?
That's a big digression, but I can spend you about 30 seconds on it to give you the 30-second version. So what you have is you have water. What you need is double heavy water, same stuff you use in nuclear bombs. What happens is a neutrino comes in with enough energy, and what a neutrino is going to do is it's going to hit a neutron. A neutrino plus a neutron can cause a neutron to decay into a proton and an electron. And so what you do is you sit there with all these neutrons in your giant vat of water. And you say, okay, I'm going to make protons and I'm going to make electrons. And so when something comes in and makes these electrons, I'm going to line my tube with photomultipliers. So I'm going to line my big thing with what's called photomultiplier tubes. An electron comes in, I apply an electromagnetic field, the electron goes towards the edge, and then I see it. It makes a big spark, big electrical signal, and I say, aha, that means a neutrino just hit my neutron and made it decay. That's how a neutrino telescope works. The biggest one, I believe, is in Kamioka, Japan, and it currently holds 10,000 tons of water. So, these are big experiments. So neutrinos, it turns out, have almost as much energy in them in the universe as stars do. Neutrinos come in at 0.3%, and all the stars in the universe, 0.5%. So it turns out that all the stuff we know, heavy elements, stars, less than 1% of everything in the universe. Most of the normal matter, most of the stuff that you and I know, is free hydrogen and helium. It's gas, interstellar and intergalactic gas. That's all it is. And yet, when we add up how much is in the universe in total matter, we find out that about 25% of the universe has to be dark matter. It's this weird stuff that we see its gravitational effects, but we can't see in any other fashion. And finally, there's dark energy, which is the only explanation we know of for why is the universe expanding faster than we think it should be. But it is, and I'm not going to talk too much about dark energy. I'm really focusing this talk on dark matter, but I can take questions at the end all night if you have. Okay. So then, what is all of this dark matter? Well, what we've said is, basically, it's this slow-moving mass. It's not moving super fast. It's slow-moving, or what astronomers call cold. And it's found in halos around normal matter. So it's formed in these roughly spherical things around galaxies, around clusters of galaxies. And it has these bizarre properties that normal matter doesn't have. First off, it doesn't emit light, and it doesn't absorb light. Well, there are many amateur astronomers here in the audience. How can you see something if it doesn't emit light and it doesn't absorb light? Really, the only thing we have to go on for this is its gravitational effects. The gravitational effects are what tell us where we learn pretty much all our information about dark matter, because it doesn't interact normally. It doesn't interact the same way normal matter does. So, to be completely honest, we don't know what it is. We know it has these properties, but we would love to figure it out. And this is what I'm working on. This is what I'd like to figure out. What is this dark matter? So what do you need to figure out what it is? Well, one option that people take is they say, well, I am just going to build the biggest, most expensive apparatuses I can think of that might do it. And so they have one in Europe called the Large Hadron Collider. And this is a 26-kilometer long particle accelerator that's built underground. It costs somewhere upwards of $10 billion to make. And one of the things they're looking for with that is dark matter. Right? This is another experiment called CDMS, which is the cold dark matter search, or cryogenic dark matter search, because they freeze it. And these are big, expensive experiments. I believe there are tens of thousands of people working on this one and hundreds of people working on this one. And they haven't found any dark matter yet, but they're looking for it directly. And they're going on the off chance, over here at this collider, what they're doing is they're saying, well, if we smash two normal matter particles together with enough energy, maybe we'll make dark matter in the lab. And what this group is saying is, well, we live in a galaxy, and we have dark matter coming in, and maybe it'll smack into one of our detectors, even though it hardly interacts at all. Maybe we'll get lucky, and it'll interact with one of these detectors, and then we'll see it. There's a drawback to this in addition to how unlikely it might be, and that is the cost of these things. These things cost a little bit of money, and and I don't have it. But what I do have is the galaxy. Okay, so this is an image of the Milky Way galaxy taken from space. Alternatively, we can use astronomical methods to try to figure out what this dark matter is. The way we can do this is say, well, we're right here in the galaxy, and we live inside this giant halo of dark matter. So if we can figure out something that would make one type of dark matter unique from another, it is all around us, and so we'll have a great chance of finding it. So what can we do about this? Well, let's take a look at what dark matter does. This is a simulation from the birth of the universe until about the present day of what dark matter does. And so you can see that dark matter starts to cluster together. So let's say that this is the halo that will form around our galaxy. You notice it's making a giant, big conglomeration, and it's attracting all the mass towards it. But I want you also to know